Good afternoon, and I'm Shengping Wang from Chiho Series 60, and this is my partner Liu Xu. And today we would like to share some thoughts about the escape technique from Docker and KVM QEMU machine. And this speech includes two parts. First, I will introduce the Docker escape technique, and second, I will talk about the QEMU escape technique. Let's move on to Docker first. About Docker. It's a container technique based on Linux. During software delivery, what Docker does is just like ocean shipping. Our operation is just like a cargo ship, and every software working as a cargo container. These containers are isolated from others. Users can easily combine the components needed together, such as development environment, email service, databases, and so on. Technically speaking, containers mean multiple applications running in one Linux operating system, which are similar to virtualization. However, they are different. It's say not that multiple operating systems built in one host server to provide a lighter weight substitution. It allows multiple operating loads running on one host machine. Therefore, Docker will save a lot extra OS resources compared to the virtualization system. Due to Docker's many new features, Docker has grabbed a lot of attention from many famous service providers, and Docker has already been widely used in cloud-native services such as SaaS and PaaS. And Docker can be named as the next generation cloud computing pattern. And after introduction of Docker, now we continue to talk about some key Docker techniques in Linux system. As I said before, Docker has isolation feature. It means each container isolates from another. One container has its own file system, process ID, user ID, memory, CPU set, and other resources for running. And these fundamental techniques are namespaces and C groups. These techniques assure the Docker's isolation of process access permissions, resources, and so on. C group is a kind of mechanism provided by Linux kernel. C groups will divide system tasks and their child tasks into different groups in order of resources. Normally speaking, C groups could limit, record, isolate physical resource used by process groups. It provides guarantee for container virtualization. Actually, C groups are a series of hooks attached on the process by kernel. When the process is running to schedule resources, it will trigger related hooks, and this will help system to trace and limit its resource. Now, I believe you have a brief understanding of Docker. Let's discuss about Docker's vulnerability. At first, about the Docker images, which is used to initialize a container. For example, some developers use Docker containers as sandboxes, and some may think that processes inside a container just are as safe as processes in virtual machine. Moreover, there are some people download unverified Docker images, run them on host machine as learning samples. There are also several PaaS services providers allow their end users upload their own Docker images. And under the multi-tenancy environment, admin can't exactly know the source of each image, but these images could do things by using the root privilege on the host OS machine. Technically speaking, namespace technique makes Docker's isolation come true. In traditional Linux system, PID is unique and isolated. In normal cases, users want separate PIDs. However, in Docker, we have namespace. It helps to let same PID could exist in different namespaces separately. Although Docker could be seen as independent space by using namespace, but Linux kernel cannot use namespace. Even there are a lot of containers, all system calls from a container are processed by Linux OS kernel. Moreover, modules like system devices and kernel modules are not fully isolated. These points bring potential risks to Docker and make Docker escape possible. Inside Docker container, escape attacks have two ways. One is from container to host, another is between containers. After escape, attacking containers can execute any command in host machine. As I mentioned before, all host operating system and Docker directories will be visible by the attacker, especially under multi-tenancy environment. When user get a container's privilege remotely, it will bring big risks. Recently, in the latest version of Docker, there is a massive security instance that an internal port of Docker Swarm could be accessed outside from the internet. So attackers can use Docker remote API to get into the Docker container remotely by Docker command without any security check. This container shell could be controlled by the attacker. Then attacker can get the host machine root privilege inside the container by Docker escape technique remotely. Based on mentioned points before, let's talk about how to implement Docker escape. First, let me introduce the container process creation in Linux. The running environment of a Linux process includes rootfs, user ID, group ID, network, process ID, devices, host info, and so on. A new Docker container process is created by calling do-fork vices colon. Here, I want to talk about the colon flags in the do-fork procedure, which determine the feature info of our fork processes namespaces. After that, inside the same one namespace, our process creation and execution inside a Docker container will inherit these namespaces features. When create an initial container process, these flags will be set. I will talk about these flags detail in the next structure. The NX proxy is a running environment for current container, and the NX proxy structure of the container is where namespaces set by the flags used in do-fork. This structure is the key for assuring container works. It's important to know that when we fork a new process inside the container, all essential info it may need will get from the structure. This structure shows our definition about the namespace, it including the UTS namespace, IPC namespace, mount namespace. Here I want to introduce the mount namespace. Mount namespace supports isolation of Linux OS file system by isolating file system mount points. After isolation, change of each file structure inside mount namespace are separated from others. Only its own file system will be affected by our mount operations of new generated namespace, and nothing to do with outside. And the rest is PID namespace and the network namespace. The network namespace is used for the network resource isolation, such as the individual network card. And the next structure I want to talk about is the task struct. The Linux kernel manages a process by task structure descriptor. A task struct contains current container's process ID and other related info of a container process. Here, the structure membership, which have close relationship to a container process, as fs struct, nx proxy, and task group. In addition, more important, the task struct of the container process is the same one seen inside and outside of Docker. This is very important for our Docker escape. The command line chroot is related to mount namespace of Docker. Chroot is used to change root directory and restrict the directory access permissions to the process. In Linux, system default directory structure starts from root directory. However, after applying chroot, system could name specific location as root directory. By means of chroot, containers could execute under different root directory. At the same time, this guarantees that container only have rights to execute their own directory structure. Here, for instance, I have two processes, PID1 and PID2. PID1 located outside of container, PID2 is inside of the container, and the directory structure of PID1 is under Linux standards such as root, home, temp. But container's work directory is under Docker rootfs. So the work directory of PID1, which is outside the container, is Linux standard directory, and it has right access directories under Docker. Actually, work directory of PID2 is Docker rootfs, and PID2 doesn't have right access to any directory other than its own directory. This guarantees processes inside current container are independent from directories outside the Docker container. The address, which fs struct finally point to, shows info related to current container process working directory. This means if the current process is inside a container, the fs structure of the container process is mapped to the file system where its container mount when created. Therefore, we can say that fs structure actually guarantees the current running container process working directory, and it won't affect other processes inside the same container. Here, I also want to talk about the differences between the fs structure and the mount namespace. The mount namespace is a shared structure. This means for running processes, mount namespace has nothing to do with them, but if we fork a new process inside a container, all required info for directory access privileges of this process need more namespace provided. Based on the above analysis, we can reach to our ideas of escape. The first step, make the container process get into kernel execution by special Linux kernel vulnerabilities exploration. The second step, change the FS structure of a current container process. Make current container process get privilege for accessing root file system of the host operating system. That means get the FS structure of process 1, the initial process of the host operating system. And finally, container achieves a global escape by changing the NX proxy namespace of the container. Let's analyze the first step. In Linux step, there is a type of vulnerability that allows a local unprivileged user to escalate their privileges on the system by system call. And in Docker container, all system calls of a Docker container finally will be proceed by Linux kernel of the host operating system. Hence that as long as the vulnerability exists in this procedure of the system call of the container, it can be used by a normal container process. So we can get into kernel by using these types of Linux kernel vulnerabilities exploration. As we see, a normal container process can trigger the vulnerabilities of Linux kernel via system call to let the shellcode executed in kernel mode. And that means a container process can execute the code in kernel mode via this type of vulnerability. After step 1, let's get into step 2, make the kernel process have the global file system access permission. That means we need to replace the FS structure of the current process with the FS structure which have the global access permission. So how we can get the init process FS structure which could access the global system of the host operating system? The answer is in kernel version before 3.0. We can directly get it via the init FS structure of the init process in the host Linux operating system. And this is the structure in Linux kernel version 2.6. But after the 3.0, we have to find another way because these structures do not exist anymore. As I have mentioned before, the task struct is the same one inside and outside the Docker container. And also, task struct is a doubly linked list structure. And in Linux operating system, all processes are generated from the initial process, which have the PID 1. So after the process get into the kernel execution, we can get init task struct by the current task struct, which PID is 1 in its list. Then get the FS structure of the initial process, point 2. And this is a code to get the FS structure of the first process of Linux operating system. After that, we can use founded FS struct to replace the current container's FS struct to make current container process get the global file system access permission on the host operating system. First, we can call function daemon FS struct to replace the current container process's FS struct in kernel version 2.6. However, after version 3.0, there's no longer this function in kernel. But we can also use functions written by ourselves to realize it. After this step, the container process can get the full file system accession of the host operating system. And the final step is to let the container escape. As I mentioned before, inside one container, all container process refer to the same NX proxy when created. Therefore, after replacing NX proxy, which current container process pointed, we can escalate a container's privilege to global. Here, we replace a current namespace by calling function create new namespace and switch task namespace to reset the current container's NX proxy. This will help container to achieve a global escape. After this step, a container finishes escape, and inside the container, create a new process means it has a full privilege of the host OS. However, after kernel version 3.0, the function mentioned above are not usually worked. Due to the security reason, many kernel functions are not exported anymore by the developer. Here, we may realize the functions and point it back, but it's not stable usually. A better solution is after the Docker container process get into kernel execution and replace the FS struct, we can open shell within the container to execute the command to mount the container's root path to let the container achieve a stable escape and get the global access privilege of the host OS. Here is a demo video about executing escape inside of the Docker. In this video, first I check the process and password directory on the host file system. Then I open Docker, get into Docker's bash and check the process and the password. Next, execute the exploit inside the Docker and get a root shell of the Linux OS system. And after the escape, we can view all the processes, including the containers processes itself. Now it's inside the Docker, and the next step is to execute the HRP. And it only has two processes. This is running the exploit. Now it's outside of Docker after we run an exploit. Now we can see that we run the PS and can get all the processes on the host machine, including the Docker process itself. And that is the Docker escape demo video. And next part, I will introduce the escape technique from the virtual machine of the KVM QEMU platform. First, let me introduce the KVM QEMU. KVM is a Linux kernel module that allows a user space program to utilize the hardware visualization features of various processors. QEMU can make use of KVM when running a target architecture that is the same as the host architecture. For instance, when running a QEMU system x86 on an x86 processor, you can take advantage of the KVM acceleration, giving you a benefit for your host and your guest system. There are three modes switched when running a virtual machine on KVM QEMU in the Linux. It's the guest mode, user mode, and the kernel mode. And our escape will based on the next 4 points. The first one is KVM QEMU memory layout. In the user mode of the host machine. And the second one is where to place the shellcode. And the third one is RAP/IP control. And the last one is the exploit details. First is the KVM QEMU memory layout. This is a memory layout of a user mode KVM QEMU process by execute the command line on the host machine like this. And in this memory layout, the letters R, W, E represented the read, write, and execute attribute of the corresponding memory area. After the understanding of this, let's go through from the beginning of the right peak, such as the LabM. This area has 4 lines. For example, the first line is a code segment. This area could be read and execute, but not writable. The second line has no attribute. The third memory area of LabM will be used to place a global variable usually. The fourth area is a heap area used by LabM. It's readable and writable. The mapped area is usually used for the emulated device of the virtual machine, such as a FIFO or a floppy disk and others. And the second use of memory map area is used for the physical memory area of the virtual machine. The heap and the stack is the memory area used by QEMU process. And the last is about system call memory area. What's interesting here is that this area is a fixed area on our 64-bit NIX version of QEMU. I will talk about this later. After the understanding of the memory layout will help we understand the following memory area to place our exploit shellcode. Unlike the traditional exploitation method, we can't control the memory allocate and free of the host machine inside a virtual machine. This causes that we cannot use the conventional heap spray method to put the shellcode. So we need to use the information leak vulnerability and unconventional methods to make our exploitation. But due to the limit of the information leakage vulnerability exploitation, we need to find more places to put our shellcode. And take a look at this pic. The physical memory area of a virtual machine is created by memory map from the host machine QEMU process. So we can place the shellcode in memory area of the virtual machine and find it on the host machine by some fixed calculation. And this is a good place to put our shellcode. We start a VM and allocate 2G memory area by this command line, and then let's take a look at the memory layout of virtual machine process on the host machine. It's apparently that address range is 2 GB, and this area will be changed when we operate the memory area inside of the VM. And let's check this. This is the base address we get from the memory layout. First, we run a test code inside the virtual machine, the code including a string like this. The second, we calculate the offset and find the string on the host memory area. And this address is the physical address of the string. After all of this, although it is a big place to put our shellcode, it's hard to get a vulnerability to leak the memory map area of QEMU. And the second way to place our shellcode is a FIFO of the emulated device. This area is also memory mapped from the QEMU process on the host machine. The Venom vulnerability exploitation in 2015 is a very famous case of the FIFO. This is peak when we verify the Venom vulnerability. The code write number 42 by the function out B to the FIFO, and in the second peak, we can find the code 42 on the corresponding memory area on the host machine QEMU process. And there are other methods to place the shellcode, such as the emulated network device RAM. It's also the ideal memory area. In these two peaks, when we pin a site, we can also find the string on the QEMU process memory. After we put the shellcode, let's take a look at the methods of EIP control to execute our shellcode. The first structure I want to introduce is the RQ state in QEMU, which is related to the callback function. In this structure, the QEMU RQ handler is pointed to an executable code area. After we control the handler directly or indirectly, we can control the code execution procedure, and that is EIP control. And the perfect status is to control the whole RQ structure and also the arguments of the handler function. And that makes the exploitation more effective. And this structure is related in the virtual hardware interrupt. We can trigger these types of vulnerability by the operation on the emulated hardware of QEMU inside a virtual machine. Let's look this function in a simple language. This is argue state pointer, and the bottom is QEMU argue handler. And what we need to do is to rewrite the Rx plus OX30 pointer to let the executable procedure change. After we rewrite the handler, we can call RBX to execute the memory area we want to. This is a similar structure can be used to control EIP, and the procedure is similar to what I said before. So I don't talk much about this structure now. And there are more ways to control EIP, such as the vulnerability of buffer overflow or use after free vulnerability of QEMU. After introduction above, let's take a look at the exploit steps. The exploit steps is just like what I mentioned above. First, we place the shellcode. Second, we trigger the vulnerability to control EIP. And third, bypass ASLR and DEP by the vulnerabilities. And finally, execute the shellcode to achieve our escape. Here, we introduce two vulnerabilities, CV 2015-7504 and CV 2015-5165. The first one is a typical heap overflow vulnerability. The second is the information leak vulnerability. Although the vulnerabilities can't leak the right address we want, in the special version of QEMU, part of the function's address offset is fixed, so we can get the best address to calculate the other address of the functions we want to bypass ASLR, and then construct the RB chain use mprotect to change the execute attribute of the shellcode to bypass DEP. Let's take a look at the heap overflow vulnerability. This is part of the code in QEMU version 2.4. Here, the array buffer overflow 4 bytes to the RQ structure when the use of the buffer is just 4096 byte, and that is what we need, like we talked before. And this link is more details about this CVE found by our team. And there are other ways to exploit during our research, like the fixed address of the system call in QEMU process. Call this address directly in shellcode will be much helpful for our exploration. And this is a sample of the shellcode to call the system call directly after we control the RBX and the RAX. And here is a demo video about escape inside a virtual machine of KVM. And in this video, we start a KVM QEMU virtual machine and run exploit code inside it to let the host execute the shellcode to attach to a remote attacker machine. And this is the attacker machine. First, we check if we could connect to the host machine directly. It doesn't work. And next, we start a QEMU virtual machine. And we run the exploit. Now the host machine, there is some stream print. And on the attacker machine, we can connect to the host and run a shell on the host machine. And this is to create a folder from the attacker machine on the host machine. And that's all in the question time.
Thank you very much for your presentation. Are there any questions?
Is it possible to break out of a Docker container if processes are not running as root?
Could you please louder?
Is it possible to break out of a Docker container from processes which are not running as root? So if you got a web server.
有没有可能 no, we should use the kernel vulnerability, and because it's a design architecture weakness of the Docker, so we make use of this. Yeah.
Okay.
Other questions? Lunch is already being served outside in the expo hall. You can enjoy your lunch while you're looking around in the expos. We'll start again at 2 p.m. Thank you.